Today is Monday. Today is Monday. Monday string beans. Are you hungry, children? Come and eat it up. Today is Tuesday.
In this video, I want to start our discussion of what it means for a module to be a free R module. This video will be a little longer because I want to talk about how this is presented in Dummett and Foote, and then also how it's presented in Conrad's introductory notes on modules, where the definitions and the notation are tied more directly to what you already know from linear algebra. Here's the definition from Dummett and Foote. An R module F is free on the subset A of F if for every element x in your module, there exists unique non-zero R1 up through Rn in your ring and unique elements A1 up through An in this subset A, such that x is an R linear combination of A1 up through An with these chosen coefficients, that x equals R1 times A1 plus Rn times An. So n is some positive integer. For every element, there's some integer n where there's this unique R linear combination of exactly n elements from A. In this situation, we say that A is a basis or a set of free generators for F. It makes sense that we say that A is a set of generators. Every element in F can be written as a finite linear combination of elements of A with these coefficients being in the ring R. So it's a set of generators. It's a set of free generators because we have this uniqueness of how to write each element as this R linear combination. If R is commutative, the cardinality of this set A is called the rank of the free module F. OK, there's something being sort of hidden here. If R is not commutative, this is more complicated, and this is something that's addressed in the exercises that I don't want to talk about. This definition would only be given here if this notion of the rank were actually well defined. So that if maybe, we've seen that an R module can have many different sets of generators. And there are examples where you have R modules that have different sets of generators with different numbers of elements. But if you have a set of free generators, in the case that R is commutative, if the cardinality of that set of free generators is defined to be the rank of F, it would be weird if you had one set of free generators of size 5 and one set of free generators of size 9. So that actually doesn't happen. And that's something that I'll talk about a little bit at the beginning of the next lecture. OK, so I want to highlight something about free modules and the internal direct sum. These are presented right next to each other in Dummett and Foote. And there's something that's potentially confusing about these two notions. So F being free on the subset A is a statement about uniqueness of elements of F as R linear combinations of elements of A. Right? So it's each x in F can be written in a unique way as R1 A1 plus Rn An, as finite R linear combinations of elements of A. What did we talk about in the last video? M being the internal direct sum of submodules n1 up through nk is also a statement about uniqueness of elements of M. But it's different. Here, the uniqueness is uniqueness as sums of elements of these submodules. So where do elements of the ring come into the uniqueness in an internal direct sum? Nowhere. This is just every element in here can be written uniquely as something in n1 plus something in n2 plus something in nk. So I really want to emphasize these notions of uniqueness are not the same. There's a good reason why internal direct sums are brought up right before free modules in Dummett and Foote. It's because there's some result that I'll talk about next time where we want to use the theorem that we just proved at the beginning here, this proposition 5, in the proof of this result about free modules. But we'll get to that later. So these notions really are not the same. I'm going to just emphasize what the difference is about the uniqueness, and then I'll give you an example after we get some more space to erase. OK, so what's the uniqueness for the internal direct sum of two modules? n1 plus n2. That is, for every element in this internal direct sum, there exist unique module elements, n1 in the first module, capital N1, n2 in the second module, capital N2, such that x can be written as n1 plus n2. No ring elements in sight here. If f is a free R module on a subset A of f, for every x in f, there are unique module elements. I really want to highlight this. So there exist unique module elements, A1 up through AN in A. So these are elements of this free module, and unique ring elements, R1 up through Rn in the ring, such that X is an R linear combination in exactly this way. So they're both of these concepts are about expressing elements uniquely, but the kind of uniqueness required is different. Okay, so I'll pause and erase, and I'll give you a more concrete example. Let's take the example of R equals Z, and Z mod 2Z is our first Z module, and Z mod 2Z is our second Z module. So we can think about the external direct sum, Z mod 2Z cross Z mod 2Z. If you think of that external direct sum having this submodule isomorphic to like anything in the first coordinate, 0 in the second coordinate, that's isomorphic to n1. We get another one, 0 in the first coordinate, anything in the second coordinate, isomorphic to n2. So we see that that external direct sum is isomorphic to the internal direct sum of those two submodules. So this is something just like what we have seen for groups when we talked about internal and external direct products of groups. So every element in n1 plus n2 has a unique representation as n1 plus n2, where n1 is in the first of these submodules and n2 is in the second of these submodules. But n1, this element in the first submodule, which I guess you can think of, if you like, as n1 comma 0, if you want to think about something as an external direct sum, that's the same as 3 times n1. No matter which of the two elements you pick in Z mod 2Z, if you take 3 times that, you're back where you started. Take -7 times that, you're back where you started. There are many different ways of taking R times one element and getting back the same element. So the elements in this n1 plus n2 do not have unique representation as R linear combinations of some integer times 1, 0 plus some integer times 0, 1. Where here I'm writing this with the notation of an external direct sum because I think it's a little simpler. So what are we seeing? What we're really seeing here is that Z mod 2Z plus Z mod 2Z is not free on the subset 1, 0, 0, 1. In fact, it's not free on any subset, but there's something that you have to prove in order to see that. Like here, we're just saying that there isn't uniqueness of R linear combinations where you take these two elements. But in fact, there's no subset you could take of this module and get something that was a free set of generators. All right, so I'll pause and erase, and then I'll go from Dummett and Foote's description of what it means for a module to be free to the description given in Conrad for what it means for a module to be free, which I like because it's more directly connected to things you know from linear algebra. Let's give definition 3.1 in Conrad's notes. Let's say M is an R module. A subset A of M is linearly independent if the only relation sum over I of Ri times Ai equals 0 is the one where each of these Ri's is equal to 0. So that's certainly one linear relation. If there are no others, if there's no non-trivial linear relation, then this set is linearly independent. A subset that is not linearly independent is called linearly dependent. What does that mean? That means that there is a relation, sum over I of Ri times Ai equals 0, where not all of the Ri's are 0. There's a R linear combination of these AIs that gives you 0, where not all of the coefficients in the ring are equal to 0. A subset A of M is called a basis if it's linearly independent and if it spans M. If it's a generating set that also has this no non-zero linear relations property. A module that has a basis is called a free module. So this should remind you of something from vector spaces. So remember, when we learn about taking linear combinations of vectors, there are these two different things. There's this no non-trivial linear relation equal to 0 that gives something equal to 0 property. And then there's this property of being able to write one of your vectors as a linear combination of the other vectors. And for a vector space over a field, these two notions are the same. What I'm trying to emphasize here is that when we go from vector spaces over a field to R modules, which is kind of like vector spaces over the ring R, those two notions are no longer the same. That it's not so clear which one you should take in order to say what the right notion of linear independence is. And it ends up being this one, that there's no non-trivial relation that gives 0. So let's first talk about the equivalence in this for vector spaces. I would imagine some of you haven't thought about this in a long time. Let's say that V is a vector space over F, and V1 up through Vn are a bunch of vectors in your vector space. If you can write one of your vectors Vi as a sum, let me say, not a sum, but as a linear combination, I'm going to fix that as a linear combination of the other Vj, then the set of vectors is linearly dependent. If you can write some Vi as a linear combination of the other vectors, then the set is linearly dependent. Why is that? Well, if Vi is equal to alpha 1 V1 plus alpha I minus 1 Vi minus 1, skip over index I, alpha I plus 1 Vi plus 1 plus alpha n Vn. Well, this is going to give us a linear relation. How? Well, this is actually just like something that we saw when we were proving this proposition 5 about the internal direct sum. Alpha 1 V1 plus alpha I minus 1 Vi minus 1 minus Vi plus alpha I plus 1 Vi plus 1 plus alpha n Vn is 0. This is a non-zero linear relation. So what did we use here? Nothing. I mean, this is going to be a property that is true, that if you're in an R module and you have a set where you can write one element of your set as an R linear combination of the other elements of your set, then that set is not going to be linearly independent. You'll get a non-zero relation, and your set will be linearly dependent. So when you're in a vector space, then this, if you can't write any of the vectors as linear combinations of the other vectors, then your set is linearly independent. But that property is not going to be true in general. So let me explain what happens for vector spaces. If you have a non-zero linear relation, why does that mean that you can write one vector as a linear combination of other vectors? So we have alpha 1 V1 plus alpha n Vn equals 0. Let's just suppose that alpha 1 is not equal to 0. If alpha 1 is 0, you could just take the first index for which alpha I is not 0. So then what can we do? We can move everything else over to the other side and then divide by alpha 1 or multiply by alpha 1 inverse, if you like. So V1 is equal to minus alpha 1 inverse times alpha 2 times V2 plus minus alpha 1 inverse times alpha n Vn. So we see that this non-zero linear relation lets us write V1 as a linear combination of the other Vi. So a sum where you have coefficients in the field. All right, but how come we can't always do this in an R module? Because this involved multiplying by this element alpha 1 inverse. And if you're just in a ring, you don't know that all of the coefficients in this non-zero linear relation if all of the coefficients in the ring that occur actually have inverses. A lot of the times they don't. So here, to say that these two conditions are equivalent in vector spaces uses the fact that we can always divide by minus alpha 1 when alpha 1 is not 0. And you cannot always do this in a general R module. So that's one of the things that is a first contrast between what's going on for R modules and what's going on for vector spaces over a field. So in the last video of this lecture, I'll give a lot more examples of things that are true for vector spaces where you need to be quite a lot more careful for R modules. Let's give an example to emphasize the point we were just making about differences between taking the vector space over a field and an R module M. M equals Z is a Z module. It's an abelian group. And the set 2 and 3 is a spanning set for M. Every element of Z can be written as some integer times 2 plus some integer times 3. This set is linearly dependent. Why? Because there are non-zero relations involving these two generators, like 3 times 2 plus -2 times 3 equals 0. But we cannot write either generator as a multiple of the other one. So what I mean is 2 is not an R linear combination of the single element 3, and 3 is not an R linear combination of the single element 2. This is different than what happens for vector spaces. So for vector spaces, if you have a set of vectors that are linearly dependent, then it must be the case that we can write one of them as a linear combination of the others. So what we're seeing in the setting of a general R module that's not necessarily the vector space over a field, these two conditions being linearly dependent and having one element that is a linear combination, an R linear combination of the other elements, these are not the same condition anymore. The main reason is that, I mean, it is true that 3 is a multiple of 2, but in Q, not in the ring Z. So now that we've talked about both Dummett and Foote's definition of what it means to be free, and then also the one presented in Conrad, let's just see how they compare. In Conrad's notes, free is saying that there's no non-trivial relations involving the elements of your set A. There's no R linear combination of the elements of A except the one where all the coefficients are 0. And in Dummett and Foote, free is a statement about the uniqueness of representation of elements as R linear combinations of the elements of your set. So these don't look exactly the same, the no non-trivial linear relation one and the uniqueness of representations of elements as R linear combinations one, but they are the same. Why is that? Well, if you fail to have this uniqueness, if there's a different way to write 0 other than 0 plus 0 plus 0 plus 0, like where all of the Ri's are 0, then what would that different way to write it be? It would be a non-trivial linear relation. But what if you fail to have this uniqueness for some other element that's not 0? Well, if you can write x as R1A1 plus R2A2 plus RnAn, and also as S1B1 plus S2B2, and so on, this is going to give a non-trivial relation. How is that going to work? You just subtract this side from this side, and you get something that gives a non-trivial relation for 0. So you'll see that failure of uniqueness gives this non-trivial relation. If you have a non-trivial linear relation, then you don't have uniqueness for 0 to begin with. So these don't look exactly the same at first, but they really are the same. So for the rest of this video, what I want to do is just give a couple of examples. So part of the point here is just to use the language of basis and spanning set and linearly independent or dependent. But I also want to give an example that I think is important to keep in mind that I want to highlight. All right, so Rn has basis E1 up through En. This is something we've already seen when we talked about generating sets. You can write Rn as RE1 plus 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 REn. R bracket x, this is another example that we talked about already. This is an R module with basis 1x, x squared, and so on. This is a set that is a spanning set, and it's linearly independent. There's no R linear combination of these powers of x that's going to give you 0, except if you take all of the coefficients, all the Ri's to be equal to 0. So the example I want to highlight is example 3.7 in Conrad's notes, where R is equal to z adjoint square root of -5, and I is the ideal generated by 2 and 1 plus square root of -5. So what is that? It's everything of the form 2 times something in R plus 1 plus square root of -5 times something in R. This is an R module. It's an ideal. So, I mean, one way to think about it is R is an R module over itself, and I is a submodule. So this really is an R module. And if you take the set 2 and 1 plus square root of -5, this is a spanning set. Why is that? Well, everything in this ideal can be written as 2 times something in the ring plus 1 plus square root of 5 times something in the ring. So everything in this ideal is an R linear combination of these two elements. But this set, this spanning set, I want to show is linearly dependent. Why is that? Well, we just have to give a non-trivial linear relation. So what we need is we need 2 times A plus 1 plus square root of -5 times B equals 0 for some elements A and B in the ring that are not both 0. Well, let's just take A equals 1 plus square root of -5 and B equals -2. And then this is clearly equal to 0. So what are we seeing? This spanning set is not a basis because it's linearly dependent. What about some other basis of size 2? Well, if you take any subset of two elements, x and y and I, you get something linearly dependent. Why? Because you just have to give a non-trivial linear relation, ax plus by equals 0, where a and b are elements of the ring that are not both 0. And you can just take a equals y and b equals -x. And that's a non-trivial linear relation as long as a and b are not both 0. So as long as x and y are not both 0, we see that this set is linearly dependent. But if x and y are both 0, then this is just 0 and 0 inside of I. We have a lot of linear relations, like 1 times 0 plus 1 times 0 equals 0. So what are we seeing is this R module, I, doesn't have any basis of size 2 because it doesn't have any linearly independent set of size 2. Okay, so it's a little exercise that you really should do, that if you have a linearly dependent set, and then you take a set containing it, it's still linearly dependent. So one thing that means is that any set of size 3 is going to be linearly dependent, or any set of size 17 or any number larger than 2 will be linearly dependent. So there are no subsets of I of size 2 or greater that are linearly independent. So the only possible hope to find a basis for I would be to find a basis of size 1, a spanning set consisting of a single element. That set of size 1, we also need to check that it's actually a linearly independent set. Okay, so I'll pause and erase, and then I'll explain why, in fact, this does not happen. So I've first written up here something that I said out loud, that if you have a subset A and M that's linearly dependent, and then a larger set B containing A, then B is also linearly dependent. Why is that? If you have a non-trivial linear relation among the elements of A, certainly you still have all the elements of A in the set B, so you do have a non-trivial linear relation among the elements of B. Just take the ones that are already in A, that linear relation you already have. Similarly, but in kind of an opposite direction, if A in M is linearly independent, and you have a smaller set, a subset in A, then that smaller set is also linearly independent. Why? Because if there was no non-trivial relation among the elements of A, if you take a smaller set of elements, you can't like suddenly acquire a non-trivial linear relation. All right, so what does this mean? We've seen that I has no linearly independent set of size 2. So it has no linearly independent sets of size greater than 2 either. So it can't possibly have a basis of size 2 or larger, because part of being a basis requires being linearly independent. So I doesn't have a basis of size 1 either. Why not? It doesn't have a spanning set of size 1. Why not? If it did, what would that be? That would be one element in I, such that everything in I could be written as something in R times that one element. But that would mean that this ideal would be principal. And we've shown already that this is not a principal ideal. So that's why there's no spanning set of size 1. So there's no spanning set of size 1. So there's no basis of size 1. There's no basis of size 1 or basis of size 2 or larger. So this I is an example of an R module that does not have a basis. So this is like a key example to know. In section 11.1, which we'll come to rather soon, we'll see that this is just not possible for a vector space, that a vector space V over a field F does have a basis. So we'll see that for finite dimensional vector spaces or finitely generated vector spaces V in the actual like body of this section 11.1. And then exercise 10 in section 11.1 deals with not necessarily finitely generated vector spaces or infinite dimensional vector spaces, where this is like a nice application of Zorn's lemma.